Welcome back to linear algebra. In this video, we're going to be talking about systems of equations. The process of solving a system of linear equations should be something you're very familiar with. You've learned in previous study of mathematics how to take a system of two linear equations in two variables and use one of several techniques in order to solve it. You've also seen how to take a system of three linear equations in three variables, use a process known as elimination to rewrite it as a system of two equations in two of those variables, and then solve for each of those variables before going back and solving for the last variable. Those techniques are the driving idea of linear equations. But one of the things that you certainly noticed in that process is that solving a system of equations in two variables is not that bad. Solving a system of equations in three variables becomes tedious. And if you have four or five or six variables, you really have to start hoping that there is some nice behavior in those equations that you can use to your advantage. In today's lesson, I want to revisit some of those techniques. I want to look at the vocabulary we use to describe a system of linear equations and start building the framework to extend these. And in the future, we're going to look at some systems that are much larger and some more powerful techniques that can solve a system much more readily. So without further ado, let me get my head out of the way and let's dive in. As we approach a system of equations, we're going to do so thinking about the solutions as a vector. So we're going to take a vector x, we're going to look at its components, x1, x2, down through to xn, and we're going to take a linear combination So if we have some c1 times our x1, some c2 times our x2, all the way through to cn times our xn, we add all those things together. We call that a linear combination of the variables x1, x2, down through to xn. Linear combinations are the heart of linear algebra. So thinking about this as building up linear combinations is the big idea. And once we have a linear combination of n variables, we can turn it into a linear equation in n variables. Let's try writing that so it actually looks like words. Right. A linear equation in n variables is any equation that we can write in the form of that linear combination equals some other constant, which we'll call b. I missed a word in that. And once we have a linear equation in n variables, we can talk about a solution. A solution to a linear equation is any vector whose components satisfy the equation. Building out from there, a system of linear equations in n variables is a set of some other number we'll call m linear equations containing the same n variables. And a solution to a system of equations is a vector which is a solution to every equation in the system. Just a little bit more vocabulary to go. The solution set of a system of linear equations is a set of vectors such that, first, every vector in the set is a solution to the system. And every solution to the system is a vector in the set. Right? It seems fairly straightforward. And again, I hope that all of this vocabulary is familiar to you. But I wanted to go through it and make sure that we're all on the same page. And I also wanted to go through it and talk a little bit about how strict we want to be with our language, right? A solution set is a relatively simple idea and an idea that you've probably used in previous courses in various different contexts. But a solution set has to satisfy both of those conditions. Every single item, every single element of the set has to be a solution, and every single solution has to be an element of the set. So if you want to prove something is a solution set, you need to prove both of those things occur. All right. I'm not going to try to write down the last definition. It's not really a definition, but when you have instructions that tell you to solve a system, the goal is to find an expression for the solution set. And as you've seen in previous study, as you've looked at systems of equations before, you should already be familiar with the fact that many systems of equations have one unique solution. Some systems of equations have infinitely many solutions, and some systems of equations have no solutions. There's not really any other choices when it comes to a system of linear equations. Linear is going to always imply there's either 0, 1, or infinitely many, which is surprisingly common in the world, so it's a nice place to start. All right, let me get my head out of the way and let's talk through the process of solving systems of equations that you already know. My notation might be a little bit different from what you've used before, but it should be a familiar concept. All right, we'll start with a relatively simple system, a system of two equations in two variables. Two x1 minus x2 is equal to 1. 3x1, I'm sorry, I think I jumped between those. 2x1 plus x2 is equal to 1. 3x1 minus x2 is equal to 4. This is a system of two equations in two variables. When you've solved a system like this in the past, you've probably written the variables as x and y. There's nothing wrong with that, except that I want you to get used to using these subscripts, x1, x2, x3, because that extends out. If we had a system in four equations, then we extend out, right? X, Y, Z, I guess we'll use W. But does W come first or does W come last? And you start to get a little bit confused about that. What if we had a really big system? There are only 26 letters in the English alphabet. What if you have a system that has 28 variables? You run out of letters. And so thinking about this using x as our variable and just subscripting it will allow us to build out our system as far as we need to. But to solve this system, the process of elimination, if I label this first equation as equation A and the second equation as equation B, you might do something like add equation A plus equation B, because 2x1 plus 3x1 is 5x1, and x2 minus x2 is 0. So you go to the right-hand side, 1 plus 4 is 5. And that gives you a very simple equation to solve. Divide both sides of the equation by 5, and we get that x1 is 1. Then we use a process called back substituting. We take that value of x1, we plug it back into one of the equations we started with. How about equation A? And we have 2 times x1, which is 1, plus x2 is equal to 1. Do that multiplication. It's very simple. Subtract 2 from both sides. It's very simple. We get that x2 is negative 1. So we have that x1 is 1. We have that x2 is negative 1. Our solution as a vector is 1, negative 1. And if we want the solution set of every solution, well, that's the only solution. So let's just put it in some curly braces. All right, let's ramp up the difficulty just a little bit, going from a system of two equations in two variables up to a system of three equations in three variables. And what I hope you notice immediately in this system is that a lot of the work has been done for us. It's a system of three equations in three variables, but the first equation, which I've labeled as A here, has all three variables. The second equation has only two variables, and the third equation has just one variable. And so if I take just equation C, I can very quickly solve and get that x3 is equal to 2. I can then back substitute into equation B. Let's try writing that so it looks like the letter B. I get x2 plus 3 times x3, which is just 2. And I can easily solve that equation and get that x2 is equal to -1. Continuing my back substitution, I can go to equation A, which has x1, has x2, which I now know is -1, and has x3, which I now know is 2. Come on. All right. Cleaning up a little bit, this is x1 minus 1, which means that x1 itself is 3. Once again, we have just one solution. I will write it as a vector. x1 is 3, x2 is -1, x3 is 2. And to write our solution set, we write the set which contains that vector. Right. Ramping up the difficulty just another small notch. Right, we're not getting into things too quickly because I want this to be a nice warm-up. The mechanics of solving a system of equations should be fairly familiar. All of the algebra that I'm doing should feel comfortable. It shouldn't be anything that you're really worried about. So I want you to think about the concepts and think about how things are linking together and think about how I'm talking about them. All right, but let's look at a more complicated system. Again, it's in a system of three equations in three variables. And to solve this system, I'm going to use the process of elimination. Call these equations A, B, and C. And we have a couple of different ways we can approach this. Maybe I'll take equation B and I'll subtract twice equation A from it. So if I leave equation B alone, I'm sorry, I'm looking at the wrong thing. I want to subtract 3 times equation A from equation B. So leave equation B alone, multiply equation A by 3, well, by -3. Add these together. 3x1 and -3x1 is 0. 3x2 and +3x2 is 0. 2x3 and 3x3 is 5x3. 16 and -6 is 10. All right, that's a useful equation that we're going to have to come back to. Let's call it equation D. I can also look at combining these equations by taking equation C and subtracting, this is where I wanted the 2 times equation A. So equation C is 2x1 minus x2 plus x3 equals 9. Minus 2 times equation A is minus 2x1 plus 2x2 plus 2x3 equals minus 4. And when I add these equations together, 2x1 minus 2x1 is 0. Minus x2 plus 2x2 is x2. x3 and 2x3 is 3x3. And 9 minus 4 is 5. Right? That's another incredibly useful equation for us. Let's go ahead and call that equation E. If you've been paying attention, you might notice something very interesting about the equations that we just derived. If I take equation A that I had from the beginning, if I take the new equation E that I just found, and I take the equation D that I just found, this system of equations is the same system of equations that we looked at in the last example. So by using this process of taking one equation in my system and adding or subtracting a multiple of a different equation in the system, I create a new equation. And if I replace those two equations that I added or subtracted to with the new equations, I get a new system. I know what the solution to this system is. I know that it's going to be 3, -1, 2. I don't have to do any more work, because if I did more work, it would just be exactly the work that I did on that previous problem. Right? That is mathematicians' favorite tricks. If you think back at everything that you have ever done in algebra, it all comes down to this process. We take something that is complicated, we turn it into something we know how to deal with, and then we deal with that. And if you really think about it, the only thing we know how to deal with is a linear equation in one variable. If you have a linear equation in one variable, you know how to solve it. If you have a linear equation in two variables, you can figure out the value of one variable, plug it in, and turn it into a linear equation in one variable, and then solve it. That's what we did up here. And again there. We had a linear equation in one variable in the first place there. If I go back to the earlier example, that's what we did. We had a system of two linear equations in two variables. We turned it into a linear equation in one variable, we solved it. We used that information to turn another equation into a linear equation in one variable, and then we solved it. If you think about high school algebra and college algebra, you learned how to solve a polynomial equation by reducing it to linear equations using the zero product rule. And then you solved the linear equations. You learned how to solve a rational equation by turning it into a polynomial equation and then using the zero product rule and turning it into linear equations. Linear equations are all we really have. And everything else is just hoping that we can get something to turn into a linear equation. All right. In the example that we've just done, I was very explicit about that. We take something that is a mess, we rewrite it, we find that it's equivalent to something we have already solved. And then I just jumped in and said, we already solved this, we know what the solution is. Formally, We talk about that as equivalence. We say that two systems, and here implicitly systems of linear equations and variables, two systems are equivalent if and only if they have the same solution set. You have probably come across this abbreviation at some point in the past, but just in case you have not, the phrase if and only if comes up incredibly frequently in mathematics, and so abbreviating it as IFF is common enough that by the time you graduate with a math degree, if you are going in that direction, or honestly, by the time you graduate with a physics degree or an engineering degree, because there is enough math in those majors, you are at the point that you subconsciously, whenever you want to say or hear or think about if and only if, you write it as IFF and you don't even realize you did it. All right, so if and only if here. If the systems are equivalent, if we know that the systems are equivalent, then we know that they have the same solution set. And uh, if we want to claim that systems are equivalent, we can do that by showing that they have the same solution set. Sometimes you'll see this referred to as necessary and sufficient conditions. It is necessary that two systems of equations have the same solution set. It is sufficient to know that two systems have the same solution set if we want to show that they are equivalent. All right, so it is a necessary condition. If it doesn't exist, then the property is not true. It is a sufficient condition. It is all you need to check to see if the property is true. That's going to be something that comes up a lot in this and every mathematics course. All right, continuing onward, I mentioned in the opening a little bit of vocabulary here. We say that a system is inconsistent if and only if it has no solution. So a system which has no solution is inconsistent. A system called inconsistent has no solution. And as a quick example here, let's take a look at the system 2x1 plus x2 is equal to 3, and 4x1 plus 2x2 is equal to 5. If I label these as equation A and equation B, we might do something like take equation B minus twice equation A. So leaving equation B alone, multiplying equation A by -2, we get negative 4x1, we get minus 2x2, and we get minus 6. When you add these together, you get 0 on the left-hand side, you get -1 on the right-hand side. That is definitely false. The fact that we are able to combine these equations and get a result that is false tells us that they do not agree. There are no points where both equations can be satisfied. This is an inconsistent system. A consistent system may have exactly one solution, or it may have infinitely many solutions. Both situations, both types of results are referred to as consistent systems. So as a quick example here, consider this system. x1 plus x2 minus x3 is equal to 1. x1 minus x2 plus x3 is equal to 3. If I add these two equations together, I will get 2x1, x2 minus x2 is 0, minus x3 plus x3 is 0, and then 1 plus 3 is 4, which gives me that x1 is equal to 2. If I try to back substitute with that, I get two equations out of it. 2 plus x2 minus x3 is equal to 1, or rearranging that, x2 minus x3 is equal to negative 1. Or if I back substitute into the other equation, I get 2 minus x2 plus x3 is equal to 3, or minus x2 plus x3 is equal to 1, and multiplying both sides of this equation by negative 1, I will get x2 minus x3 equals negative 1, which is exactly the equation that I had before. And so we don't have a unique solution that comes out of this because we only have one equation left and there's two variables in it. I can take the time to rearrange this a little bit more nicely. Generally, I would write this as something like x3 is equal to x2 plus 1, just rearranging this equation. And that would give me my vectors. The solution here is any vector where x1 is equal to 2. x2, I don't really have anything to talk about. I'll often throw a dummy variable in for that. Let's call it t. And then x3, based on the equation I have over there, must be t plus 1. And no matter what real number t you choose, this construction will give you a solution to the system. So if I build this as a set, instead of saying the word for, I guess I can use the vertical bar that is so common. The set of all vectors 2t, t plus 1, such that t is a real number, is the solution set for this system of equations. It has infinitely many solutions. Every value of t that you plug into this vector will satisfy the system. Right? The solution is not all vectors. It is a very specific subset of vectors, but it is every vector that satisfies this condition. When you've dealt with systems of equations in the past, you've generally been looking at cases where you want to have one unique solution, and having infinitely many solutions is looked at as something of a problem. There are times when that is the case, and there are also times when it is not. So one last bit of vocabulary here before we wrap up. A homogeneous system is a system of equations where each constant term is 0. So for example, this system, I have two equations with three unknowns. 2x1 plus 3x2 minus x3 is equal to 0. Minus x1 plus 5x2 plus 2x3 is also equal to 0. Right? It doesn't matter how many variables there are in the equations. It doesn't matter how many equations you have. What matters is that on the left-hand side of the equation, you have only terms that have a variable in them. And on the right-hand side of the equation, you have 0. Whenever you have that, you have a homogeneous system. Now, for every homogeneous system, there is what we call a trivial solution. That trivial solution is that vector x is the 0 vector. If you plug in 0 for every variable in the equation, it will always work out. It will always be true. The interesting question in linear algebra is, how can we tell when a homogeneous system has non-trivial solutions? That's the thing that we are interested in figuring out. If a homogeneous system has non-trivial solutions, that means that it has infinitely many solutions. And there are absolutely applications, there are absolutely times when we are hoping that it has infinitely many solutions. A quick tie-in here. If any of you are taking or will take in the future or possibly have taken in the past differential equations, one of the big ideas in the first course in differential equation is called a homogeneous linear differential equation. When you have a homogeneous linear differential equation, it turns out that there is a really nice technique that you can use to find the infinitely many different solutions to that equation. It's not a coincidence of these names. Differential equations is a very strong application of linear algebra. And if you continue onward to take a second course in differential equations, most of that course is going to be taking a differential equation and turning it into a corresponding linear equation that you can approach using the techniques of linear algebra, up to and including using computational tools, using a computer software to solve this differential equation for you. So there are applications that don't feel obvious at first of finding a homogeneous system of linear equations and looking for non-trivial solutions. We'll look at a few of them in this course. We'll look at some very abstract ideas that boil down to, does the homogeneous system of equations have a non-trivial solution or not? But for right now, I would like you to look at this particular one. I wrote the equation 2x1 plus 3x2 minus x3 equals 0. minus x1 plus 5x2 plus 2x3 equals 0. And I would like you to solve this system of equations. It should have non-trivial solutions. See what they are, write them out, see what you can do with that, and I'll see you in the next video.